Hello everyone and welcome to our engineer interview this week with Lucy Edge. Now my name's Scott and I work at Primary Engineer, and before we start I just wanted to say thank you for signing up to this year's competition. It's our 10th birthday this year, so thank you for celebrating it with us. Now we can't wait to see all of your amazing and creative ideas. You're going to get some inspiration today from our special guest speaker so you can answer the question, if you were an engineer, what would you do? Now, as part of these interviews, we're going to be speaking with engineers who work on loads of different projects, all of them showing the wonderful, interesting and exciting things that happen with a career in engineering. Now, although these interviews are hosted live, you will be able to catch them on YouTube as the recordings go up. Now, our special guest will start with a 10 to 15-minute presentation, all about the exciting world of space and satellites, and then we're going to open up to questions from the audience. If you would like to ask a question, simply click the Q&A button in Teams and type your question in there. We unfortunately can't receive audio from the audience, so just type your questions in there and we'll pass them over to our speaker. But now I'm going to hand over to our wonderful special guest, Lucy Edge.
Thank you so much, Scott, and thank you everybody for listening to me today. I do a job called Chief Operating Officer at a satellite company, at a space company. And Chief Operating Officer just really means that when all our engineers come into work in the morning, they all know what they're supposed to be working on and which projects they're focusing on. And I also make sure that they can get their snacks from the kitchen and that the toilets work, because that's important as well if you want happy engineers. So I'm going to tell you a little bit about that probably in the Q&A, but mostly I'm going to talk to you today about the rest of my career before my current job. And that is from when I was a space engineer. So today, I hope you can see my screen. I'm going to talk to you about, if it will go forward, being a space engineer. Now, I hope you can all recognise the man that I'm standing next to in that picture. That is our very own British astronaut, Tim Peake, and he has done a lot of work with schools and with students on all the exciting things you can do in space. And I was very lucky to meet Tim Peake a few times, which I've really enjoyed. So, moving on. Being a space engineer is impossible to describe. Every single day is completely different. And if I look at these two pictures here, you can see on the left-hand side a big gold thing. It looks like a sculpture or a piece of jewellery. Actually, that is a satellite. That is a big communications satellite. It's called HILAS-1. And it's the very first satellite that I was in charge of launching in my career. And the picture on the right is me when I was a lot younger than I am now doing that job. And when you look after satellites, because they're going into space, you have to make sure that they're very clean all the time. So lots of cover-up clothes, we call them clean room clothes, quite often masks and hairnets and things, just to make sure that you really look after the satellite and you're not allowed to touch it if you don't have gloves on. So you can see in the bottom of the left-hand picture, underneath the big gold satellite, is my smiley face in my little white coat and my hairnet, so that I don't put any dirt or hair on the satellite while I'm looking after it. I'm going to tell you a little bit about how satellites get onto rockets and where they go from there, because there's a lot that we could talk about, but I think that's a really exciting part of my job. And if you look at this satellite here, it's a different one from the one on the previous picture, and you'll notice straight away, this one is black, whereas the other one was gold. Now, it's the same covering, but it can be covered in different kinds of material. The most important thing is that these are like very clever coats that we put on the satellites, and they keep them cool in the heat of the direct sunlight. But when they go into the shadow, there's no sun at all, and the temperatures can drop to -200 degrees or more. then they have to stay warm as well. So these coats are made up of lots and lots and lots of layers of insulation, like your very best winter coat that you can possibly imagine, with all that breathability as well. So it keeps you cool as well when you do get hot when you're exercising. And that's what they're covered in. And this one's black. This one is the big brother of the gold one. This is called Hylas 2. And the people who look like Lego men are actually putting the petrol into the satellite. They're putting the propellant, as we call it, into the satellite. And that is there so that when it goes up into space and it leaves the rocket, it's got its own ways of moving around, pointing in different directions and allowing itself to change orbits a little bit if it needs to. It's very hard to move a satellite around in space because satellites, although they look big, are actually quite small compared to our enormous Earth and our enormous sun, which have really, really strong gravity fields that pull things around. And it's quite hard for the satellite to move. It's like having some kind of sort of magnetic pull on them almost. So here we go. This is a rocket. And what I want to show you first is what a satellite looks like when it's in space. And you can see this looks really different. This is the big brother. This is Hylas 2. And this is the black one. And you can see these sides are black. And these sides aren't. These are shiny because they need to reflect. And these big solar panels here are how we create the power. And these are exactly the same as the solar panels you might see on the roof of a house or in a factory or somewhere providing power to us on Earth. It's exactly the same technology that takes power from the sun and turns it into electricity. And these are the antennas. These are the communication systems that take your phone call or your email and it collects it from the Earth and it bounces it off these systems back down onto the Earth so that you can pass them to different places around the Earth. And that's how, when things are happening in very remote locations, or if we have bad weather events and they take out our ability to communicate, you can still use satellite communications because you can bounce a signal from somewhere on the Earth. Scott can phone me from Edinburgh and I can be in southern Australia and I can get a message because it bounces off this satellite and it comes to me. But we can't launch a satellite in a rocket like I'm showing on the screen if it looks like this. So actually, before the launch, these are folded up just like a fan, and these are flipped in. And that means that they can squeeze into that black box that you saw, and they can squeeze inside the rocket. So I'm going to pop that down there. And I'm going to show you a little bit more about that. So that rocket is inside an enormous building, and that building is 12 stories high. And the reason it's so high is because you've got to climb up the stairs and go to each of the different levels. If you look closely, if you look into the back of the building past the rocket, you can actually see the little sets of white stairs. They look a little bit like Zs, the letter Zs at the back. And they're the stairs that take us as engineers up through all of the different stories so that we can do work on the rocket at different levels. And because this is a rocket and it's full of that propellant, that petrol to get it into space, it's also a very big safety risk. It's like an enormous firework that we're standing next to with our spanners. And we have to make sure that we have got ways of escaping. So there's a big chute down the side and you can just sort of see it at the back, but you can't really see it very well. But it's like a massive sock. And if something goes wrong, we have to jump into that massive sock and we put our arms out like this to create lots of friction. And we do the same with our knees. So we look like a little frog in the sock and we slide down 12 stories. And I can tell you, doing that training so that I was allowed to go up into the top of that building was probably one of the scariest things I've done, scarier than any fairground ride. And when I got down to the bottom, I had very sore elbows. They were sore for quite a long time. So rockets are all propellant nearly, and I'm going to show you in a minute what goes on up here. But these are great big firing satellites, effectively, like a big rocket that you set off. This is all solid fuel in here. And then inside this main piece, this is liquid fuel. So when the rocket takes off and it goes into space, after a while, these solid fuel, they burn out just like a firework, and they run out of fizzle. When they run out of fizzle, they drop off, and then you're just left with this central satellite. And then all of the different engines, because there's not only the one down here, there's lots all the way through. Each one, when it finishes its phase of burning, drops off and another one starts burning. And then that drops off and another one starts burning, until right at the end, all you've got is this bit at the top. And the reason you've just got that little bit at the top is because this is where my satellite is sitting. And this is what we call the mating process. So this is where inside that really big building, we're all standing up on one of those platforms right at the top, having gone up all those stairs. And the satellite is in an enormous crane, and it's now being gently, gently, gently lowered down onto the spacecraft. And that bit you can, onto the rocket, and that bit of the rocket you can see there, that white circle, it looks a bit like a trampoline or something. That's just here. That's just here on the rocket. So all of this is burning fuel to get us into space. And it's only here that you get to the bit with the satellite in. And if I show you it from further away angle, so if we go back to that big picture from a distance, this bit here, and excuse my little squiggly black line, but this bit here is my satellite, and you can see it there going down into the rocket. All of this is very exciting and a little bit nerve-wracking if it's your satellite. They're quite expensive and lots of people want them to work. So if we're having any problems, it can be very scary. So as the crane drops this down gently, we all have our radios, we all have our phones. Everybody is very, very well prepared and practiced. And we drop this down onto the top of the rocket. And then when we've done that, we're ready for liftoff. And when we're ready for liftoff, we sit there outside on this platform, and you can see a little bit of the jungle below, because this is in South America, right by the equator, on the shoulder of South America, below Florida. And the big standing things that look a little bit like telegraph poles or something, those are great big lightning conductors, because what we don't want is that a storm comes over and sees this big tall rocket sticking up out of the jungle, and the lightning comes down and hits the rocket on the nose. So those lightning conductors, there are 4 of them around the edge, and they protect our rocket. So then what happens next is this fabulous rocket with all our signs on. You can see my HILAS sign written on there, and then that gets launched into space. And to get it to launch into space, we have to say yes. Let's go from the Mission Operations Center. This is me in the bottom right-hand corner in my little blue shirt, looking a bit nervous there with my HILAS 2 t-shirt on my back. And you can see, even though there's a very high-tech environment, actually the button I press to say go is a little coloured in keyboard button. That's all I have. So I have 2 choices. I have green button or red button, and that's all I get to say. So I get all my information on my headphones, and I have to make a decision right there. Do I want to press the green button and say go, or do I want to press the red button and say stop? And everybody has to stop. So it's a big, scary moment, that is. Now, I'm running out of time, so the only other thing I want to say to you is that although this fantastic story of this wonderful launch is in French Guiana, where I've been a number of times for launches, we have something very similar starting to happen right here in the UK now. And it doesn't look very much like this, though. It actually looks a bit like that for a satellite. That's about the size of a shoebox, that one. It's called a CubeSat. And it's launching on this rocket, which is called Launcher 1. And Launcher 1 is in this big hangar in Cornwall at the moment with that little black satellite in it that I just showed you, that CubeSat, which is called Amber. And Amber and that Launcher 1 will be attached to the bottom of the wings of this Virgin Orbit space aeroplane, and that aeroplane will take off from Cornwall Spaceport, and when it gets a bit higher in the atmosphere, it will drop the rocket off the bottom of its wing, and then that rocket will fire its engines and go up into space. So it's very similar to this model. And the way that you can think of it is, instead of these two on the side here, these two solid rocket boosters, we have an aeroplane instead. So this central piece sits under the wings of the aeroplane and gets launched into space. And I think, Scott, I will stop there.
Thank you so much for that, Lucy. That was fascinating. Even down to the fact that we use a plane to put a satellite in space. So I think we've got time now to move on for some questions. Everyone out there in the audience, if you have any questions, use that Q&A button at the top. But to start with, I have a question for you, Lucy. What do you love about your job?
Oh, goodness me. So I think the thing I love most about my job is all of the different kinds of engineers that I work with. So if you think about that question, if you were an engineer, what would you do? Actually, there are so many different kinds of engineers in the space industry. There are engineers who know all about things like propellant and rocket fuel and the complexities of that, and plumbing systems for space and how that all passes through. And there are engineers who do something called system engineering, which is about understanding the whole system, but not in so much detail. And then the kind of engineer I am is what's called an attitude control engineer.
Oh.
And what I care about is when you're in space and your satellite's here, and if it's pointing to you like this, and I want it to point just over there like that, my job is to work out what messages do we need to send to the spacecraft to make it fire its thrusters in order to turn it that way. So the great thing about my job is that I meet people with all of the different kinds of engineering backgrounds.
Yeah, because it must take quite a team to launch satellites into space. The photo you had there, even if it was one little button, which I wasn't expecting, I always thought it'd be very technical. You must work with some really amazing people. We've just got another question coming through now. This one comes from Andrew, and Andrew asks, why is the spaceport in Cornwall and not another part of the country?
Oh, that's a really good question, Andrew. So we're going to have a lot of spaceports in the UK, or we're going to have at least 4 or 5, I think, and they will probably be in Cornwall and in Scotland, and both of the locations are important. Cornwall's important because Cornwall Spaceport is right on the coast, and the satellite, which is on the rocket and on the spacecraft, needs to be launched in a place that's safe for humans. So when the aeroplane takes off and when the rocket gets dropped off the aeroplane, we want it to be over the sea. So it's less likely to cause any trouble if there is a problem, which is very, very, very unlikely. But if it is, we want to make sure it's safe. And what happens is it then turns and it moves towards a higher latitude, so higher up on the globe, so that we can drop it off in the right place. And with Scotland, it's the same thing, really. That latitude that we're at means that we, for example, are better off than southern France or perhaps northern Africa for getting into orbits that we call polar orbits. So they're the orbits that go over the North Pole and over the South Pole. And they're a very special kind of orbit because they're very useful for imaging the Earth. Because as the Earth moves around every day underneath them, the satellites keep carving out a different path across, and it's a bit like mowing the lawn. The photos they take are like mowing the lawn of the Earth, and we get stripes of images across the Earth, and across the day you get the whole of the Earth imaged. And that's why being at UK latitudes are really important, and being at coastal locations like Cornwall and like the Highlands and Islands of Scotland are very, very useful.
Fascinating. I can't wait for someone to ask me about satellites so I can say they mow the lawn from space. We've got another question coming in now. This one's from Miss Atwood. And Miss Atwood asks, what's the hardest part of your job as a space engineer, and do you enjoy it?
So the hardest part of my job, I can definitely say, is that little bit of time before the launch when some things happen that you don't want to happen. So one day when we were dropping the satellite on the crane down onto the launch vehicle, one of the crane cables moved a bit and it knocked into one of the very, very sensitive solar panels.
Wow.
And I had to decide with my engineering colleagues, but it was my decision because I was finally in charge with that green button. I had to decide whether it was safe to launch the satellite. And when you have those kind of decisions to make and you're trying and the time is precious and everyone's saying, have you decided? Have you decided yet? And you can't quite decide because you want a little bit more information, but you're not allowed that little bit more information. That's the hardest part of the job. But I do enjoy it. I think it's a little bit, if I'm truly honest, but don't tell my boss I said this, it's a little bit of an adrenaline rush. So you get a little bit excited with the, am I going to do the right thing? But also, again, it's that mental stimulation, you know, thinking hard about what's the right answer here? What do I know? What do I not know? And what can I best do in this situation?
Well, that example leads very nicely into a question that Roxanne asks, which is what happens if you decide not to launch the satellite or the rocket at launch time? What happens next?
Well, that sets off a whole sequence of very complicated events, but it depends a little bit on why you haven't decided to launch. So sometimes we don't launch because there's a weather pattern traveling through. And because of the shape of the rockets, they're very long and they're very thin. If there's really, really high stratospheric winds, so right up high in the atmosphere, it could destabilize the rocket and then it can start spinning. So if there's a high wind pattern coming through, actually we can just wait and we can decide to launch a little bit later. So that is just a short delay. Everything stays exactly where it is, and we just wait and we reset for the next day. And the only thing that really gets affected is the party that everyone wants to have afterwards to celebrate, because that has to be delayed as well. But if it's a problem with the rocket or a problem with the satellite and it can't be fixed quickly, actually what you have to do is what we call a rollback. So you take the satellite, you take the rocket back from that place with the 4 lightning conductors, and it goes on a train line, a train track, and you take it all the way back to that big 12-story building, and you put it back in that 12-story building, and you do some analysis of what the problem is. And if it's really problematic, you actually then have to do something called defuel, which means you have to suck all the fuel out of the satellite and out of the rocket that you've put in there ready for the launch. And that then causes quite long delays. So if you ever see on the news about our exciting science missions being delayed by a month or something, that's because they've had to go through this process of taking it back, emptying it all out, and actually then you have to start the whole process all over again.
Wow. Well, I mean, I'm glad there's a plan in place for what happens if something goes wrong. We've got another question here. This one was sent in to us, and it asks, who or what inspired you to become an engineer?
Oh, okay. So I studied physics at school and I loved physics. And so when I was deciding what to do after school, I wasn't sure whether I wanted to go to university or not. And in the end, my parents persuaded me to go to university. And I thought, well, if I'm going to go to university, I'm going to study what I really love. And I studied physics. And at physics, there was at university, there was a professor there called Professor Mike Cruz. Professor Mike Cruz is still in the industry, but he's probably going to retire quite soon, I think now. And he was so inspirational to me. He was the man who really said to me, you know, I'm going away for a week. And when I get back, Lucy, I expect you to have solved this problem. And I used to think, I can't. And then I thought, but I don't want to let Professor Mike Cruz down because he is such an exciting and interesting man and I want to impress him. So I would get my head down and I would start thinking, and I would do my very, very best to solve those problems. And that got me into the mindset of thinking, I love solving problems. And that's where I ended up moving into my career.
Brilliant. Well, it goes to show how inspirational a teacher can be, doesn't it?
Absolutely. Absolutely.
We've got another question here. This one's from Sandy, and Sandy asks, what happens to the parts of the rocket that contains the fuel when they break off? Where do they go?
Sandy, you are very, very on topic with this question. So this is the space debris question. And space debris is very important. It's something that was ignored in the early stages of the space industry. And the reason it was ignored was because there were so few satellites and so few rockets that it really didn't matter very much. And because of the atmosphere, which feels thin, but actually it's quite thick compared to a satellite being in space. So it's a bit like, trying to swim through custard rather than swim through water. So when you're in the higher levels of the atmosphere, that pull, that sort of custardy pull on the spacecraft and on the pieces of the rocket that have dropped off, pulls them down and they actually burn up in the atmosphere. And because they burn up in the atmosphere, they don't really make it back to Earth. Every now and then a few small pieces make it back to Earth. And that was a sort of self-cleansing situation, and there weren't very many of them. Now that's changing, of course. We all know about Elon Musk and his enormous constellations of satellites and all the rockets that are launching from all over the world, and our new launch sites in the UK as well. So the numbers are increasing, and because the numbers are increasing, we need to do a better job of thinking about what do we do about space debris. So a lot of work is now going into reusable launch vehicles. So when those pieces fall off, how do we catch them and how do we bring them back and then use them again, clean them up and use them again? A bit like buying a refurbished mobile phone or a secondhand bicycle, something like that. You want it to be lovely and you want it to look new, but you don't mind the fact that it's had one owner before you. So we're trying to do that with rockets and we're trying to do that with satellites. But by the time you guys are working, I can confidently say that we will actually be doing some recycling in space, in factories that are in space, where we capture the pieces in space and we do the recycling there with big recycling machines, because the capabilities of what we could do in space every year are improving and improving and improving.
That is so cool. You can recycle them in space. We've got time for a couple more questions, and I've got one here. How long does it take from launch to the satellite to be working in space?
Brilliant question. I love this. So the trajectory, I find it really hard to say that word, which is difficult in my job. So the launch trajectory from taking off and dropping the satellite into space. When you go to a geostationary spacecraft, so those are those great big ones like I showed you, the black one and the gold one, that move at the same speed as the Earth, so they're always over the same piece of the Earth. That takes about half an hour to get into space.
Wow.
But once it gets into space, it's still the box. It doesn't look like this yet. It still looks like the box. So you take a little bit of time. It's a few hours. First of all, you take these guys out, these solar panels. And the reason you do that is you want power. You want power more than you want anything else at the moment. Because when you've got power, you can start powering your communication system and you can start powering your deployment so that you can push these antennas out. And then when you've done all of that, you start a process called LEOP. So that's early operations planning. So in there, you start testing everything. And it's a bit like when you buy something new at home, you get a new, you get a new television and you say, right, first of all, I want to check whether it switches on. Yeah, okay, it switches on. Now I want to check whether I can surf the internet through it. Can I do that? Yeah, okay, I can do that. Then I want to check whether I can get these connections, and it will say, no, you can't do that properly because you've put the wrong Wi-Fi on. So you have to recode it a little bit. And all of that happens in about a week. So that from the point of the launch through to being ready to actually use the satellite is normally about 10 days. And then after that, depending on what you're doing with the satellite, you might spend even several months characterizing it in space. So especially when you're talking about space telescopes, like something like the James Webb Space Telescope, you would then start saying, well, we know how it behaved on the ground. How does it behave in space? Is it the same? And that can quite often take quite a few months for the scientists to decide.
Brilliant. So I think we have time for one more question, and Miss Atwood's got a question here. What skills and tools do you use most when preparing for a launch?
So, skills and tools. The absolutely most important thing is being organised and keeping good records. As an engineer, it's very tempting to tinker. To sort of go, well, I'll have a little play of this and I'll have a little play of that and I'll see what happens. And you can't do that when you're working on satellites before launch. You have to write everything down because you need to know what worked and can you repeat it. And I always think of this as I'm not very good as a cook in the kitchen. So if I do something in the kitchen and I just sort of play around and then I think afterwards, that was really good, I should do that again. If I've not written it down, I can never do it again. And it's the same with engineering. So if you've done something and you think it's worked and you want to prove that it's worked so that you can show your boss that it's worked and the people who are paying for the satellite that it's worked, you've got to write everything down. So the most important thing before the launch is really to make sure you've got good notes and good reports about everything that you're doing. And I think the other really important thing is something I mentioned at the start, and that is super, super, super clean environments. So we have these negative air conditioners that kind of suck all the particles out of the air. They take them out of the building and put clean air that's got no particles in it back into the building. So even if maybe a hair falls out of your head, or maybe somebody brings something in on their shoes and they forgot to put their shoe covers on, there's something that's sucking it out all the time. You need your gloves on, you need your hat on. If you're a man and you've got a beard, you need a little beard mask on. They're not very good looking, I have to tell you. And you need to keep all your clothes on right up to here. So as a lady, I would say, remember to wear trousers, because when you try to put your trouser suit on and you've got a skirt on, it can be quite difficult.
Amazing. Well, Lucy, thank you so much. I just want to say to everyone out there, thank you for joining us, but a special thanks to you, Lucy, for helping inspire all the engineers in the making who are out there watching this. But if you are watching this, it is your turn to come up with an engineering idea. Remember and send them to us once you're finished so that we can get the certificate sent out to you, and then we'll hopefully see you in person at our public exhibitions in May. Now, don't forget, this interview will be uploaded to YouTube in full, so if you want to share it with other teachers or rewatch it in class, then please subscribe to see when that goes live. And one other thing, did you know that we've got a podcast series? We're currently halfway through season 2 of the podcast, with episodes being released weekly. So check out our website to learn more, or just search "If You Were an Engineer" wherever you get your podcasts. Today's podcast is with Carl Starr, so if you're still interested in space, give that a listen. But for now, I just want to thank everybody for joining us, but a special thanks again to Lucy. Now remember, if you were an engineer, what would you do?